Welcome back, everybody. Welcome to the class. Is there still anybody who has a problem that he or she is not assigned to this class? It's on the waiting list or something. So all of you are actively in the class, right? Okay, because I really have to think how to organize it better because the class was too large and somehow, but you received this email at the beginning, right? Where I ask you if you're joining the first two lectures or not, right? Okay, yeah, that's really important. Okay, good. Today, since we have not seen for 2 weeks, I'm sorry for this, but 1 week you had vacation, so I think it was quite fine. I would like to ask you if somebody can tell me what we did in the first 2 weeks. So it's already 2 weeks ago, so I think it's a good idea to repeat what we learned so far. So what did we made in this class till today? Yeah, exactly. We had a seminar about how to read a paper, right? So that's basically the first lecture. Very good. Who remembers what is an aerosol? Yeah? So it's a heterogeneous mixture, right? So it's particles which can be solid or liquid, and they're suspended in air. And there's one thing more about these particles in air, because I could just take sugar, throw it in the air, and this is an aerosol or not. Yeah? Yeah, the stability. What do you mean with stability? It's correct what you're saying, but... Yeah, exactly. So they need to maintain a few hours or something in the air. So this is the stability. They not directly fall down. So if I take sugar and throw it in the air, it's a heterogeneous solid particle in liquid, or in air in this case, in a fluid, sorry. But it's not an aerosol because it's not stable. So how many aerosols do we have at this moment right in this air here? How many of them? 1, 2, 3? A lot, right? What is a lot? 10, 15? 10,000 per centimeter. Cubic, right? So 10,000 particles per cubic centimeter, and one of you told already billion. What is billion? Yeah? Yeah? Yeah, that's what... Yeah. Exactly. What I breathe over a day as an adult is about 1 billion nanoparticles or aerosol particles. So that's just normal. Did anybody of you made the homework regarding the cigarette smoke? Yeah? What are your solutions? Or explain me what was the task? Mm-hmm. After that, we got the mass concentration of smoke and we compared it with the standard. Exactly. So it was the question if somebody is smoking a cigarette, and we were telling, okay, the cigarette contains 350 milliliters of air you inhale, and in these 350 milliliters, you have 20 milligrams of tobacco particles. Then I would like to know the mass concentration. What's your solution for concentration? 5.71 into 10 raised to 7. Again? 5.71 into 10 raised to 7. 5.71 10 to 7, and then it's the unit? Microgram per meter. What would be in gram? Yeah? Okay, in microgram, but then it should be the same. In microgram, this is milligram. Okay, what do you have in microgram? It's the same. Yeah. What would it be in gram? What would your be in gram? What would your be in gram? 10 raised to minus 5. So in gram, it would be 10 to minus 5? And your would be? Ten to the power 1. Actually, that's correct, but let me check. Yeah. Okay, so 57 grams per cubic meter. Okay, that's the concentration somebody would inhale while smoking a cigarette. However, that's not the real amount this person is inhaling, because a cigarette is not a cubic meter of air, right? So your solution should be correct, and you had a typo somewhere in the calculations, okay? But this number here. Yeah, okay, then you go, right? Yeah, very good. So then I would like to know how many particles. Did you calculate how many particles are this? Yeah?
I have 7.46 times 10 to the power of.
Yeah, 7.46? Okay, I'm not sure about the 46, but 7 and 10 to the power 11. And then it's particles per. That's now important. Yeah? You know, my father always says, "Are you sure?" And then I say yes, he says, "Very, very." And then if you say yes, then it's okay. Okay, that's correct. So that's the second question. Basically, you calculate the mass concentration, then you can calculate the mass of one particle. Okay, you have the density and you have everything to calculate the mass of one particle, and then you just divide these two things, and then you get the amount of particles per cubic meter. And then, yeah?
I had a question because I didn't really understand that by smoking, is it really related to once, like once, I don't know what it's called, one row, or does the whole one puff?
One puff, yeah. No, that's one cigarette.
Because I researched and one cigarette in Germany contains 1 grams of tobacco.
Yeah, but it's not the smoke. Because the tobacco burns and creates particles, and the smoke is the solid in the cigarette, but not the amount of particles you get due to the burning, because when you burn, you create particles, okay? And the tobacco is burning and goes into a chemical reaction, which gives the solids, and this is what you have here. Actually, I'm not sure about your number if I look, because this shouldn't be not like this. 10 to the power 11 is what I have per cigarette.
Yeah, me too.
Okay, so not per cubic meter. Okay, then it's okay. So very, very no. Okay, so this is particles per cigarette. Okay. So now the question is, the last one you already mentioned, what's the last question? So now we know how many particles are in 1 cubic meter, mass concentration. We know how many particles by number we get from one cigarette, not one puff, one cigarette, and then you should compare it to something else.
The ratio with the standard 40 micrograms per meter.
Yeah, so the PM10, 40 micrograms, PM10, 40 micrograms per meter cube. And the question is, how much more is this than this, right? 57? Yeah. Yeah. And what is the number you get then? So it's a question how much more particles you inhale, right, than you should do to this safety. It's, okay. Yeah, you can. At the end, it's you have to let's say I ask like this. What is your solution? 57 divided by 40. But 57 is in grams and 40 is in micrograms. No, you cannot compare grams divided by micrograms. So you have to, whether you calculate both in micrograms or both in grams. And then you get?
My number is kind of big, 1,425,000. I don't know if it's wrong.
My number is 1.4, 10 to the power 6. So, okay, so this is with one cigarette, how much you go about this value, okay? This value is for the overall year. This is averaged over the year, okay? Because for 24 hours, you can get more particles, okay? Then 24 hours, the average is a little bit higher. But one cigarette, if you would 1 year, like all the time, smoking cigarettes, this is the amount of particles to the power 6. You inhale more than you should. And this is one of the explanations why so often people working in mines without masks were dying so early, okay? Because they were all the time access to this high amount of dust particles, okay?
Sorry, but this is for the non-filtered cigarette, right?
I don't know. That's a good homework to figure out. Check it if you find anything about it. I would assume it's the filtered one. No. It's here. It's given for one non-filtered cigarette. Yeah, but we will learn during the class why the filter is not really saving you. Okay. That's a good question. The filter is very important, and of course, the number will decrease, but not that big because you still see the smoke. And if you still see the smoke, you should be in the region of 10 to the power 6, 10 to the power 5 for cubic centimeter. Okay? So I don't know what it would be here for milliliter then, but were these, I just made the solutions here. So this should be the numbers you should have. 10 to the power 11 is the amount of particles by cigarette. 10 to the power 6 is the amount you get more than you should. And 57 grams per cubic meter is the concentration. This is calculation you should be easily able to do, right? So it's a little bit dividing and these things. And it gives a little bit an idea for numbers we are talking about. And as I said, why I was so interested in cigarette? Why I gave you an example of cigarettes? Who remembers about this? Yeah? Why? Why did I give you an example of cigarettes? Just think or just guess. Mm-hmm. 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 Yeah, okay, but now you go a little bit off topic. So everything you're saying is correct, but why cigarette? It's correct what you're saying, but why I gave you a cigarette?
It's something we are confronting with daily. If we are on the way, we see,
Yeah.
or maybe it's because of
Yeah, it's stable. You know smoke is stable, right? The size of the nanoparticles. Did I show you already a picture of related to smoke? Which one? No, it's not my brother, and it's not me. It's my brother-in-law. Okay, so it's the guy who's married to my sister, and it's on the picture you see him smoking a cigarette, and basically we could do the full class on this picture. Okay, and I will show you this picture again, again, and again, and everything you will learn, you will discover all the time new things on this picture. Okay, today I will show you this picture again. And we started with concentration and sizes, and to get a little bit an idea of concentration, sizes, and start these calculations and so on, this is why we started with a very simple. And what you should learn here, this is a lot. In an aerosol reactor, you have even a higher concentration. So any systems, which are, for example, flame reactors, create nanoparticles with higher concentrations. So wearing masks is something very, very important when dealing with nanoparticles or aerosol particles. So the point is that while you're working with chemistry, you mainly work in a fume hood and not often carry a mask. There is a reason why, or very specific masks. When dealing with aerosols, the best you should do is carrying an FFP2 mask. I will also explain you why during the lectures, and this is extremely important for daily work in the lab. Okay? So, already long introduction, but we did even more. You talked about the first lecture, but we had a second lecture, and in the second lecture we also made something else, right? We didn't talk about carbon black and these things. We talked about something else. Who remembers what we were talking about? I know that we had a second lecture because we have a video of the second lecture. So I'm pretty sure we made it. What was the second lecture about?
we talked a little bit about the status of the particles,
Mm-hmm.
how they
Mm-hmm.
most of the particles like spheres.
Mm-hmm. At least we assume. Okay, very good. So most of them are spheres. We will learn that not all of them are spheres and we have to handle them somehow. What else? So shape. Yeah?
We talked about equivalent diameter.
Uh-huh.
We say like different types of equivalent diameter on the basis of thermodynamics and stuff.
Mm-hmm. So we talked about equivalent diameters. What is an equivalent diameter? Yeah?
The particle has the physical properties of a sphere.
Yeah. So it doesn't matter which shape the particle has, but it has the same property like a sphere with this equivalent or with a given size. Okay? And for aerosols, do you remember one of the equivalent diameters? Yeah, aerodynamic is the most important because very often we're interested in the aerodynamic behavior of aerosol particles. And I don't care about their shape at this point, but what I want to know is how is this aerodynamic behavior? So, and this is where we have impactors and these things, and they measure the aerodynamic behavior. And they give the equivalent diameter of a sphere having the same aerodynamic diameter, while we also have Stokes diameter. The Stokes diameter and aerodynamic diameter is just different density. Aerodynamic diameter uses density of water. It's fixed, and the other one uses the density of the material itself, you might be a little bit wondering why using water, but in aerosol technology, it's not so easy to determine the density of a material because it's very porous structure and it's not always the bulk density, which you can easily look up in Wikipedia. And this is why it's quite good to have this aerodynamic diameter where the density is given. Okay, but this density is always larger than the one with the density of the normal material, at least if it's a solid. And this is why an aerodynamic diameter will be always a larger sphere than the Stokes diameter, the other one we talked about. Okay, what else? Equivalent diameter, because we also said something about the equivalent diameters, or we did something with it. So we also spent some time into something else. Yeah? Yeah. Exactly. So we talked about the size distribution, and the size distributions are so important for particles because aerosol particles cover a large range of sizes. Okay, it's not like here where we have plus minus 3 centimeter or 4 centimeter with the height of the students. But if you go for particles, you have 1 micron, 100 micron, even millimeter, and all this is covered in a size distribution. So it's really hard to just work with a median size as we did here. Here the median size was 400 nanometer. We will figure out if it was a good choice or not good choice. And we always have to understand that aerosol particles are widely distributed. Why this distribution is so important, or why the size? Why we put a full lecture and I really emphasize that it's an important point? Why? Yeah? The stability has to do with size, that's correct, that's one thing, that's really good. Yeah, the stability of an aerosol depends on the size of aerosols, but there's more. Yeah? Yeah, comparison is important, but there's even more, it's correct. Yeah? Yeah, it's correct, but there's even more. For health is completely correct. But I had one slide where I mentioned, yeah? Mm-hmm. Yeah, good. So for synthesizing products, the size is important. What else? There's one sentence which I really want you to remember this sentence. It was in the slides and it tells us why the size distribution or the sizes are so important. Do you have the slides there? Do you have the slides? Yeah, so there's one sentence you can tell related to the sizes. Why are the size so important? It has to do with the properties. Yeah?
Characterizing the behavior of aerosols.
Yeah, but there was one sentence in one of the slides. There was a sentence where you say, all properties of aerosols, yeah, again? Yeah, exactly. So all properties of aerosols depend on size, and some very strongly. And this is why sizes are so important. And I really like the sentence. This is why I copied it from the book. And this is why we emphasize in sizes so much. Okay? So today I would like go further, but I think it was important to make this recap since we have not seen for 2 weeks, and now we are on the same level. And what I would like to do is to go into another topic, which is extremely important, as you see, because we have 3 lectures for this. And it's directly related to the size because these properties depend on the size, but now we want to describe them somehow and how they change with size. And this is the transport of aerosols, okay? And we spent 3 classes, we could even spend more classes on transport of aerosols. And then you will also receive your first homework, right? So this is a very important topic, and this is really one of the takeaway message. And if you look in these promising empowerment I always want to show you, there is the question, okay, we want to have a good overview about aerosol technology. I hope now we are again back. We realized, okay, this is aerosol technology class. Why moving is so important, and I want you to understand that why we have 3 lectures on this, okay? And you also see that one of these 4 points, which I will always show you in each lecture, is you know how aerosols are moving, okay? This is a key message you have to take away here. Force balance and diffusion. I think you very well know force balances, right? People who had classes with me for sure know this. I don't know if anybody of you never made a force balance so far. I hardly can imagine that not, but from basic classes you should know force balances. We will talk about it. And then there is a question, what's the difference from nano to aerosol? What's the what is the difference between nano and aerosol? Or why I said what is different for nanoparticles? Is it the same aerosol particles and nanoparticles, or is there a different? What do you think? Yeah?
I think that like nanoparticle doesn't work with a gas phase.
Oh, they work. Yeah. But so it's a good idea, but they work actually.
Aerosol is mainly depending on the particles combined with a gaseous form that could be like air or
Yeah, you're right. But the same counts also for nanoparticles. Not so much. What is nano basically? A size, right? So a micron particle is nano size? Is a micron particle an aerosol? It could be, right? So the aerosol covers a large variety, and it has to be a stable particle in a fluid. So aerosol particles can be nanometer, micrometer, and so on. While nanotech, we're looking at 100 nanometer or 10 nanometer. So there we have a clear, and we have a lot of overlaps between these two things, but we also have some distinguishes. And nano is basically just a size. And aerosol is a stable, heterogeneous, solid or liquid particles with a large size distribution. And this is also something you always should care. Okay, so why moving is so important? And actually, I already made some newer pictures, but I was not able to include them in the lecture because I wasn't so happy with them. Actually, yesterday I already still saw it, and this is a picture I made 2 years ago. Even we have the light, I know, but we need it for the recording, but I think you see what I see. And I was hiking in Spain. And when I was hiking in Spain, I saw this. What do I saw? What did I saw? Yeah. No, it's not morning moist, and this you can see because of the color. What's the color of moist normally? It's cloud, right? It's more like white, right?
Sand.
It's sand, actually, right? What kind of sand?
Sahara.
Yeah, Sahara sand. So this is in Spain, and yesterday I was in Hanover. And in Hanover on the cars, you saw, because there was last week, you could read it in the news, that we had again Sahara sand here. Here it was not so much, but in Hanover you really see that all cars are dirty, all of them, okay? And they carry a lot of sand. So the question is, how does Sahara sand comes here? Does anybody of you know how we get the fall down of Sahara sand in Europe? How does it work? Yeah, wind, right? So, and this is what you see nicely here. I don't know from which year it is. I think it's 3-4 years ago. So you see Africa and you see the Sahara, and the white things you see is the clouds, okay? And you see the dust here. All this is dust. And the dust is carried away by wind, okay? So to transport particles over a long distance, wind, which is, how do we call it technically? In fluid dynamics, we don't call it wind, we call it, somebody was saying it. Anybody was saying, I think the correct word. How do we calling it? Transport, yeah, that's the general, but we have for this specific transport by wind. Velocity, it has a velocity, it's correct. Air has a velocity, but we have a more technical term for this. Because it could be any fluid at the end. What is this kind of, also when it comes to heat transfer, we're using this term. Yeah, make a guess. Do you have an idea? Any idea? Yeah, turbulence is a special case of it. It can be laminar, it can be turbulent, so it is. Yeah, it's airflow, that's airflow, but we have a more technical. Airflow is not such a technical term. Could be also any kind of fluid. Okay, help them. Convection, exactly. Convection, okay? So if you move particles, and this is an aerosol here, because it's stable over hours, okay? It's stable sand in the air, and if you want to move aerosols over a large distance, and Africa, Europe is a large distance, then we need convection, okay? Convection is the main way how to move aerosols over a large distance. The question is, I don't know if anybody of you have seen this, it can be very impressive. Do you know how long it takes? So the sand particles are carried and then they fall down. Is this a phenomena for a few minutes, few seconds, or days, hours? Days, how many? 4, okay. More or less? 1 week, okay. More or less? Yeah, if it's rain less, exactly. If it rains, it goes very fast. If it not rains, it's regularly about 1 day, 2 days, something like this, days, okay? The question is why, and I would like to take a look at it. Do you have an idea what is the size of these sand particles? Micro. 1, 2, 10, 100? Just make a guess. It's important that you get a feeling. 10 to 11. Okay, 10 to 11, more or less. 10, yeah, okay. So it's basically, and that was quite interesting, here you see again size distributions, okay? And it's the geometric diameter. It was measured as aerosol diameter, but they recalculated to geometric diameter because they have different measurement machine. And what you see here as Falcon is an airplane, and from Portugal they started airplanes, and then they went through these sand clouds because they want to understand what kind of particles are coming there, because they know the phenomena, but it was not really investigated. And this is not so far ago, so 10, 15 years ago, they started to really investigate what's coming there, and then they also have, and this is what you see here, is measurement stations, okay? They have somewhere in Portugal measurement stations, and we see they are quite small, so 100 nanometer, 1 micron, and 10 micron, not. But the question is, why are they so small? Because sand you would normally not think as a, so sand is millimeter and sand is 100s of microns. Why we have so small sand particles here? Yeah? Yeah, why? It's correct. It's the portion which is carried by the air, but why?
They have the characteristics of aerosol.
Mm-hmm.
So the force balance of the
Yeah,
buoyancy and the drag force can.
very good. But everything is correct what you are saying. But if you assume this is a sand particle, what is the difference for a large to a small sand particle, looking at this? You have any? What is the... Okay, wir gehen ins Deutsch. So what is the difference for a 1 millimeter to a 1 micrometer particle? Because there should be a difference, because I only have the 1 micrometers here. I don't have the 1 millimeters. Why not? The surface area, exactly. And what else with the surface area? The weight, exactly. So what is a fundamental thing is the ratio of surface area to volume, okay? And this changes because the equation of the sphere, what is the volume of a sphere by diameter? Who was saying? Anybody was saying? Yeah?
For diameter, it's like pi 3 cubed by 6.
D cube, D particle cube, but it's not, what? 6, right? Divided by 6, very good. So it's divided by 6, and 4 divided by 3, it is for radius. And the thing is that, so the volume scales with cube, okay? And if you have a force which acts on the volume, like gravity, it's a volume force, the larger the particle, with cube, the gravity goes, okay? But convection, drag, and these things is not a volume force. It acts on the surface of the particle. And the surface of a sphere is d square, okay? So the big guys are not carried away by the wind. They're too heavy, and if they go a little bit smaller, it's much easier for the wind because they go smaller for gravity with this and with wind like this, okay? So small particles, nanoparticles, aerosol particles, are very sensitive to surface phenomena, okay? So the surface is relatively large. So, and this has obviously something to do with the movement of particles because we have a clear filter at the end. So the big ones stay in the desert and the small ones can travel over the air, okay? So we can use this as a quite clear way to filter or distinguish or separate or whatever particles, and we will see in the lecture that these things are done. And then the question is, okay, how can we describe this? And we already had the term convections, and I really want to tell you how to describe the movement of aerosol particles in general, or particles in general. There's one equation, and all of you know this equation, and this is used to basically describe the movement of particles. Do you have an idea what is this equation? Yeah? F is equal to m.
Like force is equal to the momentum into area.
Yeah, but this is, it's correct, but from this one you can derive another one.
Like m is equal to f.
No, I don't mean in terms of geometry, but this is, it's one force. But we have multiple forces, and from this F is equal ma, you can develop a quite complex, very basic equation which describes the movement of particles. And all of you know this equation, for sure. Hoppala. Make a guess. What do you think? Yeah. Yeah, that's one force. You're correct. It's one force, but we have multiple forces, and all of these forces are covered in this equation. Do you have an idea? Do you have an idea of any equation? Just guess. Related to movement. Yeah? The friction is a phenomena within. It's covered by this equation, it's correct, but I'm basically talking about a more basic one. But it's in there, it's correct, okay? The friction basically comes from drag, okay? What kind of equations do you know about movement? That's still in a part, how to say, this is still in one of the phenomena in it, okay? But I really want to have the basic equation, or the name, you don't know the equation. Okay. Can you maybe, yeah, thank you. I was thinking somebody is watching a movie, but Okay. Then I really had to go and make this class more exercising if people watching a movie while being here. Okay. So a very basic equation, yeah?
X is equal to half of acceleration multiplied by time squared.
Yes, but this is basically to his equation, okay? So you're not far away from this, but yeah, you also had an idea? Kinetic energy is in there, yeah. No, Ergun equation can be derived from it. Ergun equation is a very special case of it and can be derived from it. So yeah, it's related. The fluid dynamics. Everybody of you had fluid dynamics, right? Yeah, perfect. Navier-Stokes equation. So the Navier-Stokes equation can we just copy-paste for particles. And this is how we use the Navier-Stokes equation. You find different ways how to express it. And the Navier-Stokes equation is nothing else than F is equal m times A. And F are different forces. And m equals A is the other half of the Navier-Stokes equation. But we do it in this way. And it's a very simple way to describe the transport of particles. And everything you learned here, even the Sahara sand, is related to the Navier-Stokes equation. What is the problem with the Navier-Stokes equation? So now I tell you Navier-Stokes equation, and now you say, okay, I can calculate the transport of particles now. So we can finish the class for today. Or is there a problem with this equation? Do I convince you that this is important for transport? You don't look convinced. Who can solve this equation? Don't remember is good. Tell me when you remember, please, because what happens if you solve this equation? You won $1 million. Okay, it's one of the fundamental problems in math, and it's one of the millennium problems which is not solved till today. Okay, so if you solve this equation analytically, you get $1 million. And that's the problem with the equation. We cannot just easily solve it numerically. So, analytically. So if the computer can do some things and we need a lot of computational power, and then it can solve this equation or help to work with this equation. So what can we do if we cannot solve an equation? How can we work with it? Yeah? Yeah. Very good. We make assumptions and we simplify the equation. And this we can do with this equation very well. And I would like to take a closer look at this equation. And basically, it's not that complicated because it has a plus, an equal sign, and a minus. And you're aware of these things. So basically, you know, okay, we have 4 different parts in this equation. One part plus another one is equal one part minus another one. And the question is, what are these 4 parts? And how can we assume and simplify? So the first thing I would like to mention is this sign here. Here, and here, and here, and here. So it appears very often. Does anybody of you know what this is, the meaning of this one? Yeah? Yeah. And what can we relate to it?
The axis on which it's
Yeah. So how many is normally considered? 3, right? So it's a 3-dimensional case we're looking. So the room here, for example, how does aerosols, right? So if I speak, I generate aerosol droplets. They are too small, you don't see them. But how do they travel to you? And you will inhale them, and I have corona, and then you also get corona. Yeah, that's how we deal with these questions, okay? So this is 3-dimensional case. Is one thing we always can do before we talk about the 3-dimensional case? What can we do with it? Yeah?
assume one axis.
Yeah. So the first thing we always can do, just to understand something, is we don't talk about three-dimensional. We can later talk about three-dimensional, but first we start with one dimension, and we calculate for one dimension because it's much, much easier. And then we figure out what do we learn from one dimension, and maybe one dimension is already enough to understand or solve our problem. Actually, the sand falling down, do you think it's a good assumption for the sand falling down? Because I saw the yellow air, and my question was, how long will this take till the particles are settled? So what is a very easy assumption we directly can do? Yeah?
We can assume the approx time.
Mm-hmm.
What approx time it will take for this settle?
Yeah, but I would like to calculate it. It's a good idea, but I would like to calculate it, and therefore I need to use this equation. But I want to understand the settling of a particle. So this guy is settling. What?
Like the particle diameter or size of it?
Yeah, this is what I can assume because we measured it, right? We have measurement data, so 1 micron, 10 micron, whatever. This is one, but I want to go more to what you were saying before. What can I easily assume to simplify this equation with the statement you made before? Because I want to understand how particles fall down. And there's already a very important information in this sentence. How many dimensions? Yeah, one, because I just want to figure out it's falling down. Of course, in reality is more movement, okay? But for just the question, it's falling down, I easily can go to one dimension and say down upwards is one dimension, and I calculate with it, and then let's see how it works, okay? Okay, so now we already are a little bit simplified. And the next question is, what is the meaning of this term, this term, this term, and this term? Does anybody of you recognize one of the terms? Yeah? Very good. How do you see diffusion? A big D, exactly. The big D is not always, but to 99%, is the diffusion coefficient. So if there is a diffusion coefficient, diffusion. So we have this term is diffusion here, okay? So in Navier-Stokes equation, we have a diffusion term. And this is what we will talk today also. What else? So this one is diffusion. Which more? What else do you recognize? Which one?
The one next to diffusion.
This one? This one, okay. No, this whole term is the diffusion term, okay? So there is a concentration in it, that's correct, because for diffusion, concentration is somehow important. But this term is diffusion term. But, yeah? This one, right? Yeah. So the first one is transient. This means if we have a change of concentration over time. Okay, if you have descent, the concentration changes over time. There's a transient term in it. Very good. So we have transient term, we have diffusion term. What else? Velocity. Yeah, the velocity is in here. And you already could give me the technical name of this term because we have discussed it here already, related to velocity. Yeah? Convection, exactly. So there is a convection term. This is convection, and convection is related to the velocity. Then we said diffusion, so we have transient, convection, diffusion, and the fourth one is one force which is not here, but for sure we have to consider that the sand falls down is drag is We will put this a minute away. Gravitational force, exactly. And we not always have gravitational force where we could talk about Navier-Stokes equation because it's also used in astrophysics. So we have a force called external force, okay? And this external force comes from an external force field. And this external force field can be related to buoyancy, can be related to gravity, can be related to electrostatic, and so on. So is drag an external force? Why do we have drag? Or what is drag? What is drag force for a sphere? Do you know anything which is in there? In the equation. What is in the equation of drag force for a sphere? The diameter of the particle should be in there, right? The diameter of the particle, like this or different. Viscosity is not in the general equation. There is something else related to viscosity, a property of the fluid. What is another property of the fluid? Density, exactly. So density divided by 2, density of the fluid divided by 2. What is with the diameter? Is the diameter just like this or is it different? Yeah, but I told that it's not a volume force. So how does it go in there then? Yeah? Yeah. And then there is one thing still missing. Yeah? The velocity, very good. Do you know how the velocity goes in? Squared, very good. And then there is a last one missing, and the last one I already heard. Yeah? The drag coefficient as a function of. So CD is the drag coefficient, but this is the problem with the equation we have. So it's a function of Reynolds, very good. So this is easy to solve, but here we have drag coefficient as a function of Reynolds. So we need to know this term to have a clear solution. And this is drag. Now you can take a look at this equation, and now you can take a look there if you find where could it be related to. So what kind of force is drag? Basically, if we okay, so this is the drag force around the particle. So if you think about the Sahara sand traveling here, it will appear drag or feel drag. Where does the drag coming from? From which term? External. It's not an external force because it's not a force field acting on the particle. Convection, exactly, because it comes from the velocity, and then we have the convection, and if it's very slow, so if we have if we are very, very slow, what does it mean for the Reynolds number? So this is very, very slow, so completely laminar flow. And what does it mean for the Reynolds number? Large or small? Small. Do you know how small? Smaller than 1, or 0.25, but smaller than 1 works good. And as long as we are smaller than 1, we are somewhere here, okay? So, and this would be then smaller than, oh sorry, not A, this would be around 1. Do you know what's the name of this regime? Yeah? Stokes regime, right? And for Stokes regime, we can say that CD equals 24 Reynolds. So if the Reynolds number would be 1, CD would be 25. This is what you see in the diagram also. And as long as we have the Stokes regime, which looks like this for the particle, and the sand which falls down is basically this assumption, we can reshape this equation. And then we put 24 Reynolds in here. And if you put in 24 Reynolds in here, you get the drag force for the Stokes. And this is 3, and then the viscosity. Now we have the viscosity of the fluid. The viscosity comes now in because it's in the Reynolds number, and Stokes mean, so drag is basically 2 things. You learned in particle technology that drag is the summation of who had particle technology with me? Yeah. Viscous force and pressure force. Viscous, okay? So in Stokes regime, we have mainly the viscosity, and this is the friction of the molecules which hold down the particle, right? So this is why we have the gradient here, the movement gradient here, and all around the sphere we have friction. What happens if I now increase the velocity? How does this image change here? So if I increase my velocity, how does this picture change? Yeah? More linear? No. More separation in the down part?
I was thinking about the eddy currents.
Yeah.
The particle.
Exactly. So it's also what you're saying there, but it's not, does not get, so the inflow is still laminar, and at one point, zack, it will detach. It's a little bit extreme now, but at one point, it will detach. And when it detaches, we have a low density area here, and this leads to a low. So low density here compared to here, and this means I have a low pressure. And this means I have this eddy formation, and this gives a pressure turn now. Now the drag force has a pressure turn because the viscosity, the friction goes all this part here. So here I still have friction and viscosity, right? But here I don't have it anymore, but I have pressure. And this cannot be described for this weird region here, but if we have a region here which is 1000 till 10 to the power 5, and this is quadratic regime. And then I have, here I have CD equals 0.44, and 0.44 would leave here to a dependency to the velocity square. Okay? So this is why it's called quadratic regime or Newton regime, because now the drag force depends quadratically from the velocity, and in Stokes regime, it's linear dependence, okay? So the dependency is much, much less for the drag force here. Okay, so this is drag force. So basically I already gave you something to put in for this term, okay? So this is a force balance we are looking here. So we're balancing different forces. And with the simplification from these weird, very general expression here for the case that we're saying, okay, we are in one dimension, the sand particle falls down, and we assume Stokes equation. We already have one equation which we very easily can solve, okay? Because I want to understand how fast do the particles settle. So I need the density, the viscosity of the air. I need the size of the particles. We have this. The viscosity of the air is, we will get it, okay? It's possible to get this information. And velocity is what I want to calculate. So so this term can be replaced now, okay? So what is with diffusion? What is the diffusion of sand particles? Or what can we do with diffusion of sand particles? What do you think? Yeah? Yeah, very good. We can ignore it. At the moment, diffusion is not that important. There will be a diffusive part somehow, somewhere, and we will take a look at it. But so far, we just want to figure out how it's falling down, and we assume diffusion is not really important there. So we ignore it. So we directly get rid of diffusion. So then I also would like to simplify, because here I'm looking at one particle. So I could look at all the sand particles and have a very complicated approach, but I want to simplify and just say, okay, I look at one simple particle. What happens with the transient term if I look at just one particle? What do you think? What can I do with the transient term if I look at one particle? Yeah? Yeah, we can ignore it, right? We don't look at a collection of particles. We don't look at concentration gradients or whatever. We just look at one particle, so we ignore transient part. So now we already kicked out transient and diffusion, and for convection we have an equation. So what we still need is external force. So which kind of external force can you imagine is important? Yeah? Gravity. So what is the equation for gravity? What is the equation for gravitational force? mg. And what is mg? Here. What is mg then? Rho v, exactly. Which rho? Sorry? 1, right? No, not 1. 1 would be, you nearly tricked me. 1 would be of water droplet, okay? Which density we're looking at? Gravity. So gravity is mass times g, and mass is density times the volume, but which density? I don't know, we're looking at sand particles. Yeah, so the density of? The particle density, okay? The particle density times the volume. What is the volume? Yeah, so it is pi divided by 6 dp3. And now I just need g, right? So I have already one equation here, one equation here, and there's a third one I need. I need another external force. Basically, you could ignore it, but I want to have it, that it's complete. I want to have it here. Okay, so which is a particle, a force, sorry, we still have to consider? Yeah? Where is friction? It's a good idea, but friction is already somewhere. Where is friction? What is friction? Drag. right? Friction is already here. Yeah? Buoyancy, exactly. So what is buoyancy? I give you a tip, a hint. Buoyancy is mg. But what is now the difference of buoyancy? Yeah, the difference in density, because g will be g, the size will be the size, this will not change. And this is why I was asking, so which kind of density do I need? The density of the particle is here. The air, and this is the fluid. So the density of the fluid times pi divided by 6 dp 3g. Okay? So because the buoyancy is the pressure which is built up because the particle takes space and the molecules want to go back into the space. And since we're in a force field, in a gravitational field, this pressure is not completely equal. But from the bottom, it will be stronger than from the top. Okay, if we would be in space, there wouldn't be any buoyancy. But here we have buoyancy, and this is the third one. So it's the fluid which wants to go there where the solid is. So we have the fluid. So I don't know what is FB, FG, and FD, right? I don't know. This one I can know, but I don't know what is FD, FG, and FB. But what can I do now with my equation? Or what can I do now with, so I gave you 3 equations, voila, and now? Yeah, exactly. So what we can say is that we have the particle. In which direction does the gravity act? Yeah? Down, right? So the gravity goes down. In which direction goes the drag? Yeah? Why up?
It's the opposite of the. If it goes down,
Genau. So if it falls down, the drag goes up. If it goes up, the drag goes down. But we know they are settling, so it goes down. So we have a drag force. And the third one is going in which direction? Buoyancy is going upwards. Is it going always upwards? What is if I have not a solid particle, but an air particle? So the density of the solid is lower than the density of the fluid. Is buoyancy then still up or downwards? Downwards? Sure? Okay. Any other opinion? Buoyancy is always upwards. Okay, it always works against the force field where it's coming from, gravity, it's coming from gravity. And so the thing is, if the bubble rises because of the gravitational force is extremely low, okay, but the forces are directing in, so gravitational force is always downwards and the buoyancy is then always upwards. Okay. So what can we do now with these 3 F? You already mentioned it, but what can we do with it, just to repeat? Yeah, so we can say Fg equals Fb plus Fd, right? And what can we do now? We can substitute, and then we get rid of this. We don't need to know them, okay? And when we substitute them, what can we then calculate? The velocity, exactly. And this is what I would like you to do. So we look at one sand particle. So this is the solid sand particle. Here you see the forces. It's in air. And here are the equations. And as you mentioned, we can sum up everything. I hope I didn't make a mistake here. No, 3. I lost the pi. Okay. Yeah, Yeah, the pi I added. D to the power 2, no. Because we have d to the power and then we have d here, so we are losing 1, okay? So we have 1 diameter in the Reynolds number, we have d to the power square, so we are losing it here. Okay. So I would like that you now give me the equation for velocity and then you calculate this for a particle which has a diameter of 100 microns. And the air velocity, the air, not velocity, the air density, thank you. You say it's 17.210 to the power minus 6. Okay, I have to look up the correct kilogram per meter second. And the density of the fluid is 1 kilogram per cubic meter. And you have to take care with the units, okay? Not everything is in the correct units. So check the units when you do the calculations. So dP is 100 micrometer. And what I want you to do is, who has already an equation? Yeah? V equal to d squared 2g okay? So something like this, okay? Right? Okay, then it's fine. And due to time, I would like to, did anybody also put numbers in there? What did you got? Ah, okay. Yeah? Okay. 0.697. So everybody who has not this number, just sit down, calculate it, and figure it out. This is the solution, okay? But I have to take a little bit look for the time. So this is the settling velocity of a 100 micron sized sand particle. This is quite fast, okay? And this is why we see the small ones, which are staying in the air, they are settling slower. And the large ones, they are not carried away, and if a few of them are taken, they settle very fast, okay? This is nearly 1 meter per second, so the rise will not take a day, okay? It will go quite fast. So the question now is, because we know, okay, this obeys here, volume to surface ratio. So what happens if I take not 100 microns, but as we saw it here somewhere, 1 micron or 100 nanometers. So what changes if I go from 100 micrometer to 100 nanometer? And there we can open a new question, because we don't talk about sand. We can do it for sand. It will give a very slightly different answer. But I would like to show you this picture now. And this is a droplet. And this is a droplet which contains viruses. It's a little bit small because a virus is 100 nanometers, so the droplet will be a little bit larger. But I just want to give you the extreme numbers of the settling times, okay? So now we think, okay, we could calculate for sand, but while I'm talking, I generate droplets. And there is a difference in droplets, and during Corona, you learned 1 meter 50 distance. And the 1 meter 50 is the solution of a force balance of this one in X and Y direction. So there we not need 1, but we need 2 dimensions. So we simplify, we go to 2 dimension, 1 is in X and 1 is in epsilon. It's easier to do both, calculate both in 1 dimension and bring them together then. And the question is, this 1 meter 50 is the answer of the question, how fast travels a droplet and how fast does it settle? And the droplets which are looked at are larger droplets. They are similar like the sand, okay? This is what I generate when I cough or sneeze. Then I generate droplets in the size of 100 micrometer. Smaller, but somehow in the size range, 100 micrometer. But if we would have smaller droplets and we have them all the time, what is their settling velocity? So what you have to do is you just make completely the same calculations. The only thing which changes is the density, which is a little bit lower, but at the end it will not change much. It will change the number, but not to the power of. Do you have an idea how much the settling velocity decreases because of going from 1 micron or from 100 micron to 100 nanometer? Any guess how much the settling velocity will decrease? 1,000, okay, to the 10 to the power 3. Okay. Any other?
10 to the power of 6.
10 to the power of 6. Any other? So if you do the calculations, you will get this number. This is 0, 0, 0, 0, 0, 0, 0, 0. And this is 10 to the power minus 7. So your 10 to the power 6 were really good because this is 3 point and the other was 0.6, so 1 digit already. And this is, so it changes 10 to the power 6 because of the influence of the diameter square, okay? So this is not really a settling velocity anymore, okay? This does not really settle. And that's the problem when you have these small particles. And this is, again, now we look again at cigarette smoke. So is anybody smoking? I already asked, but I always forget. Is anybody smoking here? Yeah, you're smoking. Okay, so now we imagine you take a cigarette and you light it. So what would we see? Smoke. We would see smoke. And would these particles settle down? They go, huh? They go up, they go, we will talk about this, but will they settle? No. And the thing is, what changes is the number of concentration. But you can imagine everybody of us spits out droplets the same as we would smoke all the time, okay? And it will not settle easily down. And this was a little bit an open question during these 1 meter 50. What is the impact of these really small ones? They evaporate and you don't know how they evaporate and how they really travel and all these things, okay? So to a certain extent, we can use a force balance to directly know, okay, how fast a droplet will settle. But if we go to the really small ones and also the sand dust, which is 1 micron or in this range, it settles extremely slow. And this is why the sand falls down for days, okay? And there is a very nice other application, and I want to finish this one, and then we are done for the class today, because we need a little bit time in the beginning to repeat, but I think it was important to take this half an hour to repeat, right? Because of the 2 weeks break. Yeah, good, okay. So this is a complete different application now. What do you see here? A painting, very good. What kind of painting? A sunset. Ah. So you can go out every day. What is the color of the sky? What? What did it, I didn't hear the first one. Red-orange. It's here, it's red-orange. But normally, if you look now, it's blue. Why? Yeah, it's sometimes gray, okay. In Germany, it's gray. Why it's blue? Two. What is reflecting the light? Or who is reflecting the light? Yeah, the particles. So in the atmosphere, we have particles. And these particles are like small mirrors, and they reflect the light. And this is called ray light scattering. Okay, and the ray light scattering is a dependency wavelength to the particle size and then the intensity. So you will get different colors depending on the amount of particles. So we are not very good, or we are very good, of course, we are scientists in data to how climate and all these things develop. But these paintings are a very good source of climate research. Why? Because this is from William Turner, and he's a very known, if you go to England, in the, I don't know, the Museum of Arts there, what's the name, but there you will find a lot of his paintings. And we can take the paintings as kind of images. So people make a photo of the sky, and then we can refer it to particle concentration at this time. Because from the color, we can calculate the concentration, so we have a color here. But artists are weird guys. What is the problem if an artist just draw a sunset? What could be a problem? I said artists, sometimes artists could be weird guys, let's say it like this. Because of what could be a problem here? Or what could be a problem if you are, I don't know, yeah?
They add their own touch.
Yeah, they add their own touch. That's the thing. That's a very polite and nice description about it. So it could be that the artist just has the idea to make the sky green, but it is not green. And this is like a problem I cannot figure out. So what do you need? You need to calibrate your system. Like you go in a lab, and the first one is you calibrate, okay? Because it could be that also your measurement system doesn't work. And the nice thing of Turner is he made a lot of paintings from sunset. And this is like adding his own touch. So we figure out how he is doing this. And this looks quite normal, right? It's not like adding weird green or pink or whatever. And if you compare a lot of his pictures, you see that he is painting different phenomena correctly. So this is a clear sky with a little bit of red. And this is a very red one, and the red one can be connected to a volcano eruption. Why does a volcano eruption gives a red sky? Yeah? Yeah. So we add more and more particles into the atmosphere. This will influence the raylight scattering, and this will lead to a red sky. And if we have painters who over a long period made a lot of these paintments, we can take this as a hint to other data we have from these references, like stories, like ice from the Arctic or whatever. Okay, so this is a very valuable thing or nice hint to understand these things. And what is important and why it's connected to what I'm telling you here, so okay, the sky is red, but there is another information you see on the slide, and this is a very important information. What is the difference between these two? Or basically, it's not the difference, it's an information you have in the right picture. Very important information. Yeah? There's no tree here. But I'm not enough an artist to make an analysis of this. But you're right, there's no tree, but I'm referring to something else.
The time in which years in which both the paintings.
Yeah. The painting is 2 years after the eruption, and he still sees a red sky. And the volcano eruption spits out particles 32 kilometers in the air. And if you assume nothing like the desert sand traveling, if you just calculate the settling velocity, so you can say, okay, roughly 15 months, the particles were just falling down from the eruption. So when you know, okay, 15 months is the time. And 32 kilometers, you can get a velocity, right? And with the velocity, you can calculate now the size. Okay, and this is what I want you to do as a voluntary homework. what is the size of the particles which were spit out by the volcano? When you know, you can assume just 2.2 or 2.7. You can assume 2.7. It's a rock solid. Fluid of air, you can take 1 or you can neglect it. Very often buoyancy is neglected. Velocity, you get 15 months is the time, and 32 kilometers is the distance, and the rest you can figure out. And what I want to know is dP. So what was the size of the particles the volcano spits out that we have 15 months of settling, okay? And if you are able to do it, then you understand all these things here. And if you forget one of the numbers, just assume, okay? If you don't know, then take the sand solid or whatever. At the end, the magnitude should be the same, okay? If you forgot 2.7 and you calculate with 2.5 density, the magnitude should not change. Any questions to this? Good. Then I would like to also advertise a book. I don't know if this book is in English translated, but you see here, I mean, having a red sky is nice, okay? But the phenomena is one thing and the impact is another thing. And basically it means we inject nanoparticles into the atmosphere, and if we do this, they stay very, very long. And we don't know what they do all next to a nice red sunset. And there is this book, it's a science fiction book, and he is basically talking about what happens, because what happens if we have more nanoparticles in the air? What happens? Yeah, so it could be colder, and already some clever people have the idea to inject more and more nanoparticles to the atmosphere to cool down the planet. Because for the first time we had in April 30 degrees in Germany, and that's not normal. I'm grown up here and I know how April normally looked like, and not like this, okay? And then there's a very clever idea what, why not just inject more? And this is what he's dealing. In this book, he's dealing with the idea that some countries develop drones which go in the atmosphere and just spit out nanoparticles to regulate the temperature. And this is a big problem here, the settling of it, right? So, and we not fully understand these things. And that's, again, a big problem if we do these things before understanding. And this is what you see also here. Who knows who's this? Yeah? From Star Trek, exactly. Do you know his name? In Star Trek or in reality? William Shatner is reality or the actor, right? The actor is William Shatner, and he is known for, in Star Trek he is, it's the old one from the 60s, or I don't know, 60s, 70s, the really old one. He's Captain Kirk, okay, one of the most popular characters in Star Trek, Captain Kirk. And you see him, he's over 80 already, and you see, do you know where he's sitting? In a spaceship, exactly. Do you know why he's sitting in a spaceship? This is William Shatner as a real person, over 80, he is in a spaceship. I think he didn't pay anything for it. He got money for putting this slide, what he has in his hands. I will show you in a minute what's detailed on it. But his mission was, why people send Captain Kirk to space? No, that's not for science. It is not for science. As far as I know, it is not for science. So what is the idea, the general development in space, in the industry about spaceships? What is the aim of these companies? That everybody can use it, but this is basically, they have let's say, a bigger aim. This is one big step for it. But they have, like Elon Musk, and so they have this idea that, yeah? Yeah, they want to go to another planet. They want to go to Mars. That's the first idea. On the way to go to Mars, they want to go to Moon. And there are these companies, Elon Musk or Jeff Bezos, they want to do these things. And therefore, they need a lot of money, of course, because it's very expensive to go to Mars. And to get money, you somehow have to earn money, and you have to develop your technology on the same way, right? So they think space tourism is a very good idea to make money. And they say it's very important. And if you think back, depending on your age, but I still remember the time when flying was not 20 euros, okay? When flying was very expensive. And already a few people on business travel or going on vacation, which were flying, and it was always a big event if somebody as a child could tell, hey, I was in an airplane, okay? Nowadays, it's very normal to be in an airplane. And this development they want here. So there were the people coming up who were the first time in a spaceship, and then everybody goes for 20 euro into a spaceship. And this is also what he's saying here, that he's saying, and this is why they want to make marketing for it. And it's a very clever marketing idea to take Captain Kirk, and then he has this. So this is the most important and a practical concept for space use and for adding and saving planet Earth. So he says the best thing we can do, I really would like to know if it's really his opinion or if he got a lot of money for this. I don't know, but it would be really interesting. But he says the best thing is we can develop cheap space travel and send people to space. But what is if a rocket goes into space? What happens? Yeah? A lot of energy will be used, and what else? Yeah. So this is always imperfect combustion, and a rocket always creates a lot of particles. And where are these particles synthesized? It's nothing else than these carbon black reactors. It's the same, basically. Nothing else than a candle with soot, okay? And where are they produced? Yeah, and where is the fuel? Engine, and where's the engine? And where is it? Yeah? In the space, exactly. So it's a big difference if we create these particles here on the ground or if we create them in the atmosphere, okay? Settling velocities and these things. So it's a really big difference if we do this here or not. And it's really questionable if it's a good idea to make a tourist attraction about these things if we don't know the impact. I don't say that it has to be a bad impact, but we don't know it. And first of all, we should know about this movement of particles, what are they doing there, and all these things before we inject them completely in the atmosphere. Okay? So with this, I would like to end the lecture for today. Actually, I planned a little bit more, but I think the recap was good, and I don't want to stress the time too much because we still have the seminar. Next week, we will have a seminar, just for those who are not coming, with the University of Arizona together. Okay, so we will meet students from Arizona on Zoom here. So we shifted a little bit later to 5 o'clock because there is a 9-hour, but I will tell you the details in the seminar, but it's voluntary for you. Okay, but after the lunch break, I will tell you the details. So to recap, I hope you have a little bit an idea how particles move. Okay, and why it's important that particles move. We looked at a very simple example of settling down, of sand, but you see how fast it goes into health and droplets, and now we're talking about climate, and we are not here at the reactors at this point, but what you really should know is particles move because of the Navier-Stokes equation, or the Navier-Stokes equation describe how particles move. And we cannot solve it, but we can extremely simplify it. And with simplifying it, it will give very valuable numbers for our solutions. So let me check here. No, here. So I think I made the point of why moving is important. Force balance, diffusion, we will see next week. And the impact on nanoparticles, we also will see next week. So I suggest to make half an hour lunch break now. And then we meet at 12:30 here and discuss the paper, okay?